Okay. First off, are there any questions? How about homework 3? I said it was due what, Monday? Okay, any problems with that? Questions? Okay, so we're ready to go here. So the last thing we were talking about was MG1 and Benish's formula. So this is where we stood. So we're starting now, part of this is a review, of MG1 FIFO. And for that we saw that the waiting time distribution function, given as Benish got it by inverting the Polacek-Hinchen formula, is given by the following. It's the summation of 1 minus rho to the j times h tilde star j of t summed over all j from 0 to infinity. Where the h tilde of t is equal to 1 over tau times the integral from 0 to t of 1 minus h of x dx. So in these formulas, rho is the utilization of the server, and it's equal to the arrival rate times the average service time, and is assumed to be less than 1, or you don't have an equilibrium solution. And h tilde is given by this formula. The tau here is the average service time. The h is the distribution function of service times. And so the h tilde you'll recognize is the forward recurrence time of a renewal process in which the renewal intervals are the service times. And the star j means convoluted with itself j times. In other words, this thing here represents the distribution function of the sum of j independent, identically distributed random variables, each of which is distributed as the forward recurrence time of a service time. So we can interpret all the terms in the formula, but still we can't put it together or see why it is that that should work. So what we want to do is we want to explain this. In the process, I'm going to give a completely different derivation, totally different from the straightforward derivation, which is to find the Laplace-Dirichlet transform and then to find its inverse. Now I want to recognize here, by the way, that if I take the transform of h tilde and call it eta tilde, because we already know this result, then that's equal to, if I took the transform on the right-hand side, I would get 1 over tau, 1 minus eta of s over s, where eta is the transform of h, and eta tilde is the transform of h tilde. Now we know, of course, that I could always write the waiting time distribution function as follows. The probability that the waiting time is less than or equal to t, that's what this stands for, is equal to the probability that the number found by the arriving customer, the test customer is j, times the probability that the waiting time for that customer is less than or equal to t, given that he finds j, summed over all j. That's the theorem of total probability. That's always true. The question is whether it's useful, whether we can get any information, whether we can use it. Now, the interesting thing is this. If we look at this answer here, we see that this thing, the probability that n is equal to j, is exactly that if we have MM1. In other words, if I had a single server queue with Poisson input and exponential service times and calculated the state probabilities, as we know from earlier in the course, that turns out to be the simple geometric distribution. So if we have MM1, then this probability is that. Now in addition, if we have MM1 this probability is this. Why is that? Well, first of all, let me write down that this is for MM1. In fact, it's for MM1 FIFO, of course. What this says is that if I know that the test customer finds J in front of him, then how long does he have to wait for service? Well, if he finds J in front of him, that means that he finds J minus 1 on the queue and 1 in service, and there's our guy right there. So that means that the length of time he would have to wait is the sum of these J minus 1 service times for each of the customers on the queue, plus the partial service time of the customer that he interrupts when he arrives. Now, if the service times are exponential, then the partial service time and the full service time have the same distribution by the Markov property, and so then the waiting time for that customer would be the sum of these J full service times or J partial service times. Since they're the same, it doesn't matter. And so then this result would describe it in the case in which the H was in fact exponential. But here's the interesting piece. If the service times are not exponential, then this is not that, and this is not that. Nevertheless, this formula is true. So the question is to explain how that happens. And the answer is, the strategy is, well, there must be a reason for it. It couldn't just happen by coincidence that when I get all done with a whole lot of work that somehow or other, if I guess wrong here and wrong here in a sense, that is, if I put the exponential here and the exponential here, even though it isn't right piece by piece, except when the service times are exponential, nevertheless, when I multiply everything out and add them up, I get the right answer. So there ought to be a way directly of getting this answer by using the fact that somehow or other this looks like a state distribution, and somehow or other this looks like a waiting time distribution. Okay, so that's the problem. And as I said, if you look in the books that were written around the time, people were aware of this result, but they didn't know how to explain it. And there were some wrong answers given or some bizarre answers given. Everybody knew there was something there, but it was hard to figure out what it was. Finally, the answer was given by Kelly in his book. I think it was published in '79 or so. And what Kelly said is, instead of looking at waiting times, so he says waiting times in MG1 FIFO are the same as remaining work in MG1 LIFO preemptive resume. Preemptive resume. Okay, so there are two pieces here then. One piece is to convince yourself that this is a true statement. And then the other piece is to say, okay, so what? And the so what part is, well, if the waiting times are the same as the remaining work, if the waiting times in this model are the same as the remaining work in this model, once we understand that, then it may turn out to be easier. In fact, it is easier to analyze MG1 LIFO preemptive resume and find the distribution of remaining work and then interpret that as the waiting times in MG1 FIFO. So first thing I have to do is convince you that remaining work and waiting times are the same thing in the two models. Now this is a rather strange model, MG1 LIFO preemptive resume. And it's of interest in its own right. Because what happens in the LIFO preemptive resume model is when a customer arrives, he immediately enters service. If nobody's there, then he just enters service as he ordinarily would. But if somebody's in service, then that customer is bumped out and goes to the head of the queue. Then if another person arrives while this guy is still in service, then he is pushed to the head of the queue and this guy is moved back one position, and so on. And finally, when somebody leaves service, then the guy who's at the head of the queue re-enters service, and he continues his service from where he left off. So he still gets the same total amount of service, but now his service time and his waiting times are mixed up together. And so it's not clear exactly which one provides a better service, which method. And in fact, that's a question we'll get to. So in the MG preemptive resume, the virtue of this, from the viewpoint, if this model exists for its own sake, is that when a customer arrives, the server for him is always available. So the arriving customer gets service immediately. Now, if his service requirement is short enough, then it's not likely that he's going to be bumped from the server. And that means that short service time customers are going to get very good service because they're going to enter service immediately. On the other hand, if his service is too long, or if he's unlucky, somebody will interrupt him and then he'll be bumped back. And then he has to wait, and when he re-enters, he might be bumped back again. And in fact, the customer who's bumped in front of him might be bumped and so forth. So he might go back and forth, get a partial service time, then get bumped and go back and forth and so on. So that means that what's going to happen in the MG1 LIFO preemptive resume model is that short service time customers are going to get better service than they would here, but long service time customers are going to get worse service than they would here. And so the question then is, well, which dominates? But our interest at the moment is not in that. Our interest is in recognizing that these two things are the same, and then analyzing this and interpreting it this way, and that will give us Benish's formula. Then we'll ask the question about which of these models, the FIFO or the LIFO, is better from the viewpoint of the customer. Okay, so let's draw a graph of remaining work. So here's time, and here's remaining work. First thing to realize is that remaining work is the same no matter what the queue discipline is. Because what happens is, well, let's say a customer arrives, and the remaining work, that's the amount of work that, or the amount of time it would take the server to finish serving all the customers who are waiting if no new customers arrive. So if the system is empty and a customer arrives, the remaining work jumps up by the service requirement of the arriving customer. And then the server starts to serve that customer, so the remaining work works off linearly, 1 unit of work per unit of time. So the slope of -1. And then if another customer arrives, the remaining work then jumps by the amount equal to the service time, or the work brought in by the new arrival. And so you get a diagram that looks like this sawtooth diagram. In fact, this time from when the server first becomes busy until it becomes idle again is called the busy period. And it's obvious that it doesn't make any difference the order in which I serve the customers, because whenever a customer arrives, he increases the remaining work in the system by his service time. But since the server works at the same rate for every customer, it doesn't make any difference which customer is being served. The graph is still going down at the rate of 1 unit of work removed per unit of time. So all these systems have the same remaining work graph. Okay, now suppose that we were looking at MG1 FIFO. At MG1 FIFO, when a customer arrives, the amount that he has to wait is the remaining service times of all the customers in front of him, which is everybody in the queue, which is the remaining work. So when a test customer arrives, the remaining work at his arrival time is his waiting time. So therefore, if I can calculate the remaining work at an arbitrary time, then I'm also calculating how long the customer would have to wait if he was served in a FIFO queue. If he joined the end of the queue and didn't get served until all the customers ahead of him were served, and no customer that arrived after him would be served ahead of him. Okay, does that make sense? Okay, so the argument is that remaining work in every case is invariant. And in particular, remaining work is the same as waiting time if the waiting times, if the service is in order of arrival, if it's FIFO. So since we can consider remaining work in any case and equate that with the waiting times in MG1 FIFO, we will consider the remaining work in MG1 LIFO preemptive resume, because even though that seems like a rather strange way of conducting business, it turns out to be the simplest model to analyze. Okay, so now we shift our attention to MG1 LIFO preemptive resume. Okay, so let me erase this diagram right here. I'm not going to use that anymore. And now let me go into the argument for MG1 LIFO preemptive resume. Now the argument is intuitive. So that means that if you didn't already know what the answer was, you might be in doubt, especially since the result is going to be somewhat surprising. But this answer can be obtained by other methods, and you have to convince yourself that these kind of arguments make sense, because these are the kind of arguments by which you can cut through things in queuing theory, because you can get your answers without doing a lot of algebra. So you're trying to be clever instead of using brute force. So suppose I drew a picture of the state diagram. So what happens is, it looks sort of like this. The customer arrives, you jump up by 1 unit. This is the this diagram is the number in the system versus time. And then you stay in that state, and then maybe another guy arrives, and you stay in that state, and maybe somebody leaves, and so forth. So in general, no matter what kind of system you have, if customers arrive one at a time and leave one at a time, then the state diagram is going to look something like this. Okay, so let's look at a particular part of this diagram. Someplace along the line, you're going to see something like this. Let me see if I get a better piece of better. So let's say that this is level J, right there. So this corresponds to a customer who arrives, finds a system at level J, and then makes it jump to J plus 1. Okay, so that, if I look back from the diagram now, I'm going to ask myself how that could have happened. And there are two possibilities. One is that previously the diagram looked like this, and the other is that previously the diagram looked like this. In other words, if this is level J, then either I jumped down from level J plus 1 at the previous transition point, or I jumped up from level J minus 1 at the previous transition point. So what I want to do is I want to write the probability of this in terms of the probabilities of that. That's going to give me an equation, and that equation is going to produce this. Okay, so here's the argument. I say, first of all, let's look over here, and let's look at a point at which a jump occurs. Now, if a jump occurs, what's the probability that it's a jump up as opposed to a jump down? And my claim is, well, 1/2 of the jumps are up and 1/2 of the jumps are down. For every, if you look at the diagram, for every jump up, sometime later there must be a jump down. There's a jump up, there's a jump down. There's a jump up, well, sometime later I'm going to come jump down. As long as I'm in equilibrium, so that every busy period ends, that means that in every busy period, when I get to back down to 0, the number of ups and number of downs must be equal. Okay, so the probability is 1/2 that it's a jump up. Now, given that it's a jump up, in other words, given that it's an arrival, what's the probability that it's an arrival that finds the system in state J? Well, that's what we've earlier defined as pi sub j. Pi sub j is the conditional probability that given that an arrival occurs, that the arrival finds the system in state j. So 1/2 pi j is the probability of that piece of the diagram. Okay, so you can see why I say this is really an intuitive argument now. It's hard to make this mathematically precise when I talk about things like the piece of the diagram. Okay, but 1/2 pi j corresponds to what's in that circle. Okay, now, how could I have gotten there? Well, let's look at the bottom transition first. So I'll say, well, at the previous transition, that could have either been an up or a down. So the probability that it's an up is 1/2. Now, if it was an up, that is, given that it was an arrival, then in order to have taken this path, it must have been an arrival that found j minus 1. So I multiply that by the conditional probability that given that we have an arrival, it's an arrival that finds a system in state j minus 1. Now, if it finds a system in state j minus 1, then in order for this piece right here to merge into that piece, what must happen is that the next arrival must occur before the service time ends. If not, then I don't jump up, I jump down. Okay, so what's the probability that the next arrival occurs before the service time ends? Well, first of all, how long is the service time? This is an arriving customer, and if it's an arriving customer, then since we have MG1 preemptive resume, LIFO preemptive resume, that means that he immediately enters service. So if he immediately enters service, then his service time begins from the beginning. So the probability then that his service time will occur before the next arrival is this. Here is dh of x. That's the probability that the test customer's service time is exactly x. And 1 minus e to the minus lambda x is the probability that the next arrival occurs before that service time. Okay, remember that the inter-arrival times are exponential. We have Poisson input. So this is the probability that the arrival occurs prior to time x. And then this is the probability that the service time is equal to x. And now I have to add this up over all x from 0 to infinity. Okay? Remember that this x is measured from the start of service. So as soon as this test customer arrives, finds a system in state j minus 1 and arrives, he enters service. This is the probability that his service time lasts exactly x. This is the probability that the next arrival occurs prior to the end of that service time, which will then cause the diagram to jump, and I will get the piece that's in the circle. Okay, so now I got to worry about the path that goes down. Could take that possible path. So now the argument is similar, but there's a little interesting piece here. First of all, with probability 1/2, the previous event is a departure. Now, if it is a departure, it must be a departure from state j minus 1, j plus 1, which means that it must be a departure that leaves behind j. That probability is pi j star. Okay, we've defined previously the stars represent the probabilities left behind by a customer, and without the star represents the probabilities found, or the states found by a customer. So pi j is the probability that if it's an arrival, it occurs and finds a system in state j, and therefore causes a jump up, that is, occurs just before the jump up. If there's a star on it, that means that it's a departure that leaves the system in state j. So this is the probability just before a jump up from state j. This is the state probability just after a jump down from state j plus 1. Okay, so I'm taking two different viewpoints. Here I'm looking from the viewpoint of the arriving customer. That's with jumps up. Here I'm looking at the viewpoint of the departing customer. That's from a jump down. And the definition of this is the probability that just after a departure, the system is in state J. Okay, now, if that happens, that means that we're taking this path. But we still have one thing that must happen, which is that the next arrival must occur before the end of that service time in order to get a jump up, just as before. But now, how much time does the customer spend in the server? Well, it's not h of x. It doesn't have that distribution anymore because that's the distribution for a customer whose service starts at the beginning. And this customer is one who was bumped earlier and is waiting on the queue. Okay? If the system, if a customer, if the system drops down by 1 unit, what that means is that somebody left. And if somebody left, then the next customer to enter the server is someone who's waiting in the queue. And everybody who's waiting in the queue is someone who has been bumped at least once. So I don't know how much remaining service time that person has. The only thing I know is that his service time distribution function is different from a customer who's just at the beginning because he's already had some service. And I know that all of these customers who are on the queue are statistically identical. Because once a customer is bumped, then his remaining service is not affected by anybody who is behind him. And so therefore, whatever this guy has, that's not affected by this guy and so forth. So my claim is that I'm going to write an integral analogous to the one above it, except that instead of h, I'm going to use what I'll call h tilde, or h caret, or h hat, or something like that. Little caret. Okay, so this is the distribution function of the service time that starts at the beginning. This is a distribution function of the remaining service time from somebody who previously has been bumped. And that's all we know. Why is there a 1/2? Well, the 1/2s cancel out.
Yes, it's not necessary.
Well, I don't know whether it's necessary or not.
This is IJ is the probability when a new customer found system J.
Well, yeah, but remember that the pi j's are conditional probabilities. The pi j is the conditional probability that, this is the way we derived it originally, that given that an arrival occurs, in fact, the way we derived it was we said the probability that an arrival occurs in a little interval of length h, and then we let h go to 0. And when we let h go to 0, that forced the arrival to occur at a particular point t. So we said this is the conditional probability that given that an arrival occurs, at the instant at which it occurs, it finds a system in state J. And similarly, this is the probability that given that a departure occurs, that at the instant of departure, the number of customers remaining is exactly J. So there does seem to be a condition in there. Now, I have to agree with you that I found this a little bit flaky myself, and I couldn't really decide whether the 1/2 belongs in there or not. At first, when we originally published the paper, the 1/2 isn't in there. And we just said, of course, in a paper, you can't make the argument that I'm making. You can only say a few words. So you say things like, then defining these to be such and such, we see that the following relation holds. And if the 1/2 should have been there and canceled out, you can say, well, I canceled it out. And if it should be, if you put it in there, if it doesn't belong, it doesn't hurt anything because all you're doing for some reason is multiplying everything through by 1/2. So in the published paper, the 1/2s aren't there. But when I explain it, I put the 1/2s there and then I cancel them out. But your argument points up the problem that what I'm saying apparently makes some kind of sense but you're really not sure if it's absolutely correct. And that's the way it is with these probability arguments. I think you have to look at it sort of from a physicist point of view, at least as I see it, which is, yeah, you have mathematical arguments, but you have to sort of weigh the evidence. The mathematical argument may not be completely rigorous. If it doesn't work out, if you have evidence that opposes this, then I don't know. In the end, somehow or other, through consensus and through different lines of reasoning, you finally agree on what you think is the right answer. In this case, whether we put the 1/2s in there or not doesn't make any difference in the answer. And as I say, it's going to give us something that Kelly had already derived by a different method. So that being the fact, with Kelly having done it first, you can say this is an intuitive interpretation of his result. If it had not been done first by Kelly, you could say this is a conjecture that the answer is such and such, and now let's see if we can prove this by a more rigorous argument. That's the way I look at it anyhow. Okay, so now I want to do some manipulation with this. Okay, so this is pretty clever and insightful if it works. So the first thing I'll do is get rid of the 1/2s, so they don't matter. Now we can't solve this for the pi's unless somehow or other we relate the pi star to the pi's. But we already know that in any system in which the jumps up and down are of unit size and you have equilibrium, that the pi j's and the pi j stars are equal. But actually this is even stronger in our case. It's not just the probabilities are equal. Let me show you what I mean. First let me write it down. Pi j star is equal to pi j. All right, so what that means in effect is that I can simply erase that star. Okay, but now why is this? Remember how this queue works. A customer arrives, and if somebody's in there, let's say when he arrives, the system looks like this. Well, when he arrives, then all he does is move everybody back one. So that guy goes there, that guy goes there, that guy goes there, and so forth. Now, this is our test customer, let's say. He just arrived and he entered the server, and those were the number of customers that were present when he was there. When he leaves, exactly those same identical customers will be there, because if he gets bumped back into the queue, those customers will go with him. And so they move back and forth like this. But when he finally leaves, the customers that he leaves behind are exactly the same identical customers that were there when he arrived. So it's not just a probability statement, it's a stronger statement. It's a statement that the exact same customers are there. So obviously then, if that's true, then the probability that he finds J and the probability that he leaves J must be the same, because he's going to find and leave exactly the same customers. Okay, so now let's take this equation and rewrite it. Now we have pi j is equal to, now when I multiply this out, I'll multiply everything out. Why be fancy here? Pi j minus 1 integral 0 to infinity times 1 times dh of x minus pi j minus 1 integral 0 to infinity e to the minus lambda x dh of x. And the same thing is true for the second term, except that instead of pi j star, I'll write pi j because of this statement right here. And then for the 1, I've got the integral from 0 to infinity of 1 dh caret of x minus pi j integral 0 to infinity e to the minus lambda x dh caret of x. Okay, now the first thing to recognize is that this integral, of course, is 1, because I'm integrating the distribution function of something over its whole range of definition. And similarly, this piece is also 1. Even though I don't know what h caret is, it's still a distribution function. And therefore, if I integrate it over its whole range of definition, it's 1. Okay, now, what about this piece right here? Well, that piece can be viewed as a Laplace-Dirichlet transform of h evaluated at lambda. So I'll call that eta of lambda. In other words, if eta is the Laplace-Dirichlet transform of h, then this is that transform with s equals lambda. This turns up over and over again in queuing theory, is that the probability of a random variable being greater than x, that's probability that there's at least one arrival in an interval of length x, excuse me, none. This is the probability, the Poisson probability of no arrivals in an interval during a service time. And the probability of no Poisson arrivals during a random interval is a Laplace-Dirichlet transform of the distribution function of the length of that random interval evaluated at the arrival rate. So the fact that that's a Laplace-Dirichlet transform is just really lucky. All right, now how about this one? Well, that's a Laplace-Dirichlet transform too, except that we don't know of what. So let's just call it eta caret. So by definition, eta caret is a Laplace-Dirichlet transform of h caret. Okay, so let's do a little bit more arithmetic here now. Let me erase this. Okay, so writing all this out, I get pi j is equal to pi j minus 1 minus pi j minus 1 eta of lambda plus pi j, that's this one, minus pi j eta caret of lambda. Now these pi j's cancel, and what I'm left with is an equation that gives me pi j in terms of pi j minus 1 and eta caret. So I'll erase this. And I solve this equation for pi j. So I put this pi j on the left-hand side, and then I divide through by eta caret. And so what I get is pi j is equal to, the denominator is going to be eta caret of lambda. That's going to be multiplying, and that is going to be, and the numerator is going to be pi j minus 1 minus pi j minus 1 times eta. So I'll factor out the pi j minus 1. So I have 1 minus eta of lambda, and then there's my pi j minus 1. So I have pi j in terms of pi j minus 1. And this is valid for j. If you go back to the original argument, j equals 1, 2, and so on. Okay, so this is really helpful looking. This is really optimistic now, because what we have here is we have a recurrence relationship for pi j in terms of pi j minus 1. So that means that I can solve this, and of course what I get is the familiar geometric distribution. I get pi j is equal to this thing right here, 1 minus eta of lambda divided by eta caret of lambda to the j power times pi 0. In other words, pi 1 is equal to that thing times pi 0. Pi 2 is equal to that thing times pi 1, which is that thing squared times pi 0, and so forth. Okay, so that's easy enough. So we have pi j in terms of pi 0. Okay, but what is pi 0? Well, by other arguments, we know that regardless of the Q discipline, regardless of anything, pi 0 is the probability that an arrival finds a system empty. So it's, because we have Poisson input, it's the fraction of time the system is empty, which is 1 minus the carried load, 1 minus the utilization. So we've already argued many times using Little's theorem and so forth that pi 0 is equal to 1 minus rho. So what that means is, okay, what does that mean? What we know now is that pi j is equal to 1 minus eta of lambda over eta caret of lambda times 1 minus rho. Okay, let me go back and let's see, what do I want to erase? I'll erase this piece right here. Now, we know that from normalization that the sum of the pi j's as j runs from 0 to infinity must equal 1. So if I sum these guys, what that implies is what? Well, that implies that, I forgot this j here. That implies that 1 over 1 minus the thing that's in parentheses times 1 minus rho, which will factor out when I put it in this sum, must be 1. In other words, let me write this out. That means that 1 over 1 minus that thing, that's that, times 1 minus rho equals 1. Because when I substitute this into here, the 1 minus rho factors out, and this is a geometric series. And so the geometric series sums out to 1 over 1 minus the thing that's being raised to the power. Okay, so what does that mean? That means that the thing that's right in here apparently must be rho. Because I have 1 over 1 minus rho times 1 minus rho is 1. That's the only way I can get 1 out of this. So the implication of that is that the thing that's in parentheses, which is that thing right there, is equal to rho. So that implies that 1 minus eta of lambda divided by eta caret of lambda is equal to rho. Now, is that amazing or what? Because this says that in this LIFO preemptive resume model, no matter what the eta is, the ratio of 1 minus eta evaluated at the arrival rate over eta caret evaluated at the arrival rate is constant. It doesn't make any difference what h you give me. If you give me 2 different h's, I'm going to have 2 different etas and 2 different eta carets, but their ratio must still be rho. In other words, there's an insensitivity here. All right, what's the next step from here? The next step from here is to recognize, okay, so where are we? That means that the thing that's what I just erased, it's being raised to the power, must be equal to rho. Okay, so what we just did was we showed that this thing right here is rho. So what we know is that pi j, I just erase it, is equal to rho to the j times 1 minus rho. So what does that mean? Well, that means that we have just proven that for mg1 LIFO preemptive resume, the 1 minus rho, rho to the j, the geometric distribution that fits in here, is in fact the state probability. Okay, because that's pi j. That's the definition of it. The probability that the arriving customer finds j other customers. Okay, so we know that this is true for MM1, but what's amazing is it's also true for MG1, LIFO, preemptive resume. So I'll get back to this point in a minute, but this shows that for MG1 LIFO preemptive resume, the state distribution is insensitive to the service time distribution. In other words, it doesn't make any difference what the service time distribution is in MG1 LIFO preemptive resume. The state probabilities are still geometric. Okay, so we proved insensitivity here. Insensitivity. Okay? So this is a major insight from this about MG1 LIFO preemptive resume that we didn't start out to worry about, but this just drops out. So when you think about it, it seems strange. It looks like it would be very difficult to prove that something is insensitive because you have to show that no matter what service time distribution function you choose, that you always get the same answer. But we did that by just assuming it was something called H and everything else dropped out. It turned out it didn't make any difference what the H was. No matter what it is, we still get this. Of course, the service time is in here in the average service time because rho is equal to lambda times tau. Tau is the average service time. But what it says is the state probabilities depend only on the average, which is basically a scale factor, and not on the variability of the service times. Okay, so that's remarkable. That's actually the, I guess, the second time we've seen that. The first time we've seen this is in the Erlang B model, where we saw that the answers were insensitive to the service time distribution function. And in that case, you verified it also. I proved it, and you verified it through your simulation homework. Okay, let's go to the next step. So I think I'll erase this. Let's see, what do I want to erase? I can erase all of this stuff. I just didn't want to erase that because that's just too pretty to erase. Okay, so what we have, I erased it, so let me put it back. We just proved that 1 minus eta of lambda over eta caret of lambda is equal to rho. So now I'm going to solve this thing for eta caret. So I get eta caret of lambda is equal to 1 minus eta of lambda divided by rho. Okay, but what's rho? Rho is equal to lambda tau. So I'll write that as 1 minus eta of lambda divided by lambda times tau. Okay, does anybody recognize that? This thing looks just like this thing. The only difference is, which may be a critical difference from a mathematical point of view, is that this is defined for all values of s. This is defined only for a specific value of s, namely when s is equal to lambda, the arrival rate. But what that shows you is, at least for that one value of s, that the eta tilde and the eta caret are the same thing. Okay, so this appears to imply that eta caret is equal to eta tilde. We know it's true when s is equal to lambda because we just derived it. Now, if I looked at a sequence of models with different values of lambda, then of course this would be true for every one of them. Of course, this is only good as long as lambda is less than 1 over tau. Otherwise, you don't have stability. So now comes one of these tricky analysis arguments using complex variable theory. I never really understood this. This is branches off from my education in a sense. So people claim by something called analytic continuation okay, what that means is that, well, somehow or other, these functions involved are analytic, that is, certain properties in the complex plane. And if two analytic functions agree on sets that are sufficiently dense or compact or whatever, then they have to agree everywhere. So then the argument goes that since this function and this function agree for all lambda or s less than 1 over tau, then they must agree everywhere, and therefore they are equal. I'm not sure I buy that, actually. And when we first did this, I went to somebody from the math department. Let's see, this was 86. Where was I in 86? I don't know. Anyhow, I went to someone, it was here, I guess. Anyhow, I went to someone from some math department, and I asked if this was true, and the answer was, oh yeah, of course, analytic continuation. And I said, well, okay, but can you give me a theorem in a book that I can reference so I know that it's really true in this case exactly? And the answer was, well, it's got to be around someplace. And anyhow, the answer is no. Nobody could actually, or no one that I know could actually tell me for sure that this was right. So I don't really know if it is, but I'm not sure if it matters in this context, because at the very least, what this thing does is it certainly suggests that this is true, and then says to someone who cares about the mathematics of this stuff, okay, this is, we think, is a true statement. We think this is a theorem. Now I need a rigorous proof of this theorem. Now, why is this important? This is important because this has meaning. This is the Laplace-Dieltjes transform of a forward recurrence time. This is a Laplace-Dieltjes transform of something we don't know what it is, but remember how it was formed. It was formed by saying that whenever a customer re-enters the server, if you don't know things like how many times he's been bumped, we didn't know that. All we knew is that if a customer enters service from the queue, then since we didn't know what his remaining service time is, we called it eta tilde. So what that says is that in MG1 LIFO preemptive resume, if we look at a random instant, a random customer re-entering the server without knowledge of how many times he's already been interrupted, all we know is that he is just entering the server and about to begin his remaining service time. His remaining service time is the forward recurrence time of a renewal process formed by the service times, which is exactly what you would guess if you had to guess something. If I had to say, I have to come up with an answer for how much time remains for this guy when he re-enters service, I'd say, well, I'll take the forward recurrence time of the service time, because we know he's been interrupted. We just don't know how many times. So that's amazing in itself. So now what we've done is we've shown that two things. Okay, wait, excuse me, let me go back. Now what does that mean? That means that in MG1 LIFO preemptive resume, when somebody arrives, that's the distribution of the number that he finds. Now, if he finds that much, how much remaining work is there? Because remember, what we're doing is we're calculating remaining work, because we already argued that remaining work in MG1 LIFO preemptive resume is the same as waiting time in MG1 FIFO. So the question is, this is the probability that he finds J, and now I want to ask, if he finds J, how much work remains at the time he arrives? And the answer is, well, when he arrives, the amount of work that remains is the remaining service time for each person who's in the queue, the sum of those. And those are independent, and each one of them has Laplace-Dieltjes transform eta tilde. But we just argued that eta tilde is this, eta caret, hat. I keep getting the names of these hats mixed up. We just argued that, let me start this again. When a customer arrives in MG1 LIFO preemptive resume, then, or when he leaves, when he arrives in this thing, he immediately enters service, and everybody else moves back one position. Now, the question is, aside from his own service, how much time would it take to serve all of the remaining work? That is, how much time would it take to serve the remaining service time of this guy, plus the remaining service time of this guy, and so forth? And the answer is, well, those are independent, and so we want to know the sum of those j independent variables. But each of those variables has a remaining service time whose transform, by definition, is eta caret, which we proved is the same thing as eta hat, which means that if I invert this, the distribution of the remaining service time for everybody on the queue is the forward recurrence time. And therefore, forward recurrence time of the service time. And therefore, the remaining work in the system found by a customer who finds j, which occurs with this probability, is the sum, that is the j-fold convolution, of the remaining service times of each of the customers that he finds in the queue. So, this thing obviously is remaining work in MG1 LIFO preemptive resume, because that's the state distribution, and that's the remaining work given that state. And by the argument that the remaining work is also the waiting time, therefore, it's the waiting time. So we couldn't get the waiting times by interpreting term by term unless the service times were exponential. But we can get the remaining work by interpreting term by term, whether the service times are exponential or not. And in part, that's because the state distribution in LIFO preemptive resume is the same no matter what the service time is, and is exactly the same as the exponential. So the whole mystery is solved. Or maybe it's deeper. I'm not sure whether it's solved or it's deeper, but what we've done is we have we have obtained the waiting time for MG1 FIFO by instead interpreting waiting time as remaining work, and then recognizing that in MG1 LIFO preemptive resume, the state probabilities for that model are this, and the remaining work is this, and therefore the sum of the product of that times that must equal the remaining work, which therefore must equal the waiting time in the FIFO queue. So we did get a term-by-term interpretation, but that required us to equate remaining work with waiting time rather than to be able to interpret it directly in terms of waiting time. So what this shows, in a sense, is that MG1 LIFO preemptive resume is actually more basic than FIFO, because the FIFO model is much more complicated. The FIFO model has a complicated state probability. We don't know what it is. And it has a complicated piece here, which we don't know what it is. But if instead of having first come, first serve, or FIFO, first in, first out, we have LIFO preemptive resume, then this piece is simple and insensitive, and this piece is simple. So that indicates, in some sense, that this is really the more fundamental model. So why do we consider this to be more fundamental? Probably just because of our human nature, which is that somehow or other, if you're going to wait online, well, damn it, the person arrives after you, we shouldn't get served ahead of you. That's just fair and just. But that really has nothing to do with the mathematics of the situation. The mathematics of the situation says that it's much more basic and fundamental to serve the customer's LIFO and have every customer have immediate access to the server than it is to make them wait in a queue one at a time. Of course, you go to Publix and try telling people this. If you barge in front of them in the bakery, then you will die. But if they don't kill you and they listen long enough to hear this argument, then I'm sure they'd be convinced. All right, now this raises another question. The question now is, let's go back to the original model and compare MG1 LIFO preemptive resume with MG1 FIFO. And ask which is better. In other words, if I'm designing a bakery in Publix, I don't have a choice here. I have to go with FIFO. But suppose I'm designing a computer system. Okay, this is a computer operating system, say. This is a CPU, and I can have my jobs served in order of arrival, or I can have them served this way. The advantage to this is, for short jobs, is that to them, there's never a queue because they always enter the server immediately. So the short jobs get good service, but the long jobs get worse service, get bad service, because once you get bumped, then you might go back and forth, back and forth. Who knows how long it'll take before you finally get your service and get out. So the question is, overall, which one is better? Okay, any questions before I erase this? And then I'll ask your opinions.
It seems to me that no matter what kind of models you choose, the waiting time for the one server support are the same.
The waiting,
Your service times and your utilization is fixed.
no, the waiting times in the two models are different. It's the remaining work that's the same. The waiting times are different.
Yes, the remaining work for every model.
It's the same. Remaining work is the same. Right.
Since the total is fixed,
Right.
the service is fixed, but the remaining
Correct.
is the same
That's right.
every model.
Right. But the waiting time is not the same. Okay. So the question is, from the viewpoint of the customers don't care about the remaining work. The customers care about how long they wait. So what I want to do is I want to compare, let's say, the expected value of the waiting time in MG1 FIFO with the expected value of the waiting time in MG1 LIFO preemptive resume. Okay? And so there are several possibilities here. What are they? Well, the waiting times here on average, we're talking about averages, so FIFO could be greater than LIFO, in other words, worse. Could be better. Could be equal. Right? How many people think that the waiting times in FIFO are worse than in LIFO preemptive resume on the average? One. How many people think better on the average? 0. How many people think the same on the average? 1, 2, 3, 4. Okay? Now, how many people realize that there's actually another possibility?
Depends.
Depends, yeah. It depends on the service time distribution. You switch to depends?
Yes.
Okay.
Yeah, I'm switched.
You know, depends is a brand name for a product. You don't want to be involved with that, though. Okay, so depends. Now the question is, how does it depend? Well, we know that that from L equals lambda W, we know that the average waiting time is proportional to the average queue length. And the average queue length we can calculate from the state distribution. Now, for MG1 LIFO, different service time distributions don't affect the queue length distribution because we already found that it's insensitive to the service time distribution. So MG1 LIFO is exactly the same as FIFO if the service times were exponential in FIFO. If the service times are more variable than exponential, then the L gets bigger in FIFO, which means the waiting time gets bigger in FIFO. And if the service times are less variable than exponential, then the other way around. So the answer is this. The expected waiting time in FIFO is greater than the expected waiting time in LIFO if the variance of the service times is greater than the mean square. Wait, do I have that right? Let me think a minute. This means that the service times are more variable than exponential. And if they're more variable than exponential, as the variation goes up, then the waiting time goes up. So if the service times are more variable than exponential, then it's better to use MG1 LIFO preemptive resume. On the other hand, it will be less, that is, it's better to use FIFO if the variance of the service times is less than tau squared. So for example, for constant service times, it would be better to use FIFO. But for service times that are highly variable, worse than exponential, it's better to use FIFO. And of course, the answer is that if they're the same, then it doesn't make any difference. If sigma squared is equal to tau squared. So there's some qualitative insight. Okay? And from the point of view of the average waiting time, if the service times are highly variable, then it's better to use LIFO preemptive resume. If the service times tend to be not very variable, it's better to use FIFO. And if the service times are totally random, that is exponential, then it doesn't matter which one you use, at least in terms of that measure. Now, you might be concerned with other measures, tails of the distribution, but then you need more analysis. Okay, so there's a lot of stuff that you can come out of this without very much mathematics. The whole thing is based on that diagram, that equation that related the pi's and the pi j stars. The whole thing was based on this piece right here. Everything was in there. The rest of it, after he wrote that, was just turning the crank and realizing what the implications were. Okay. So, anything else about that? Okay, so if not, we're ready to go on to the next topic. The next topic, I'd like to skip to page 222, exercise 12. And so I'll just start talking about what it is, what the problem is. And I have a homework problem based on it. So I'll pass that out so you can start looking at it now, but I won't really get to discussing it until next time. This has to do with what's called vacation models. So let me write down where we are here. All right, so I'm talking about exercise 12, which is on page 222, 223. And it's, I'll call it MG1 with vacations. And this will be homework 4. So part of homework 4, the first part says do exercise 12. So I'm going to do part of this in class next time. But if you want to get ahead of the game, do exercise 12. Exercise 12 is pretty long. On the other hand, you have the answers because the whole thing is in the solutions manual. So what I'd like you to do is I'd like you to do the problem, see if you can do it on your own. If you need to use the manual, fine. I don't hand in something that's a Xerox copy of the manual solution, okay? But the solution is there. All I'm asking you to do is, by writing it out in your own words, so to speak, I'm forcing you to actually go through it and understand every piece. In the homework assignment, there are 3 parts. The first part is do the homework, which is for which you already have the solution. And then part 2 is to prove something which is one step beyond the homework, which really should have been in that exercise, except that I didn't really understand this well enough at the time. And then the third part is a numerical calculation based on that new fact. New fact is easy to prove, but it's very important. Okay, so let me explain what a vacation model is. Vacation model is a generalization of ordinary MG1, except that now you allow for interruptions in the following sense. We're going to look at one particular kind of vacation model, which says that what happens is that whenever the server becomes idle, here's a picture. Let's say that here's a busy period. And by the way, we're going to discuss busy periods in some detail soon. But let's say here's a busy period. This means that that at this point, the server has become idle. Now, in ordinary MG1, what happens is, as soon as the next customer arrives, the server starts to work. So the amount of work remaining jumps by the service time. And if it's ordinary MG1, the server starts to work on that. But if it's a vacation model, the server, when it goes idle, takes a vacation, which means that it goes away, and maybe during the vacation time it's busy doing some other work, going to some other queue, for example. And so when customers arrive back at the primary queue, if the server is on vacation, then they wait there. But the server doesn't work on them, so the remaining work remains constant and goes like that every time a customer arrives until the server returns from vacation. When the server returns from vacation, then it starts to work, and it works off the work just like before. So if we had a vacation model in which the server returns from vacation always at the instant that the next customer arrives, then the vacation model reduces to the ordinary MG1 queue. But if the vacation, which has a general distribution, that is, you can specify vacations in different ways. If the vacation doesn't end with the arrival of the first customer, then there's work queuing up while the server is not available. So when the server starts to work, the length of time it's going to take to finish all that work depends on how many customers arrive during the vacation. Okay, so the question is to figure out what the effect of the vacation is, and surprisingly, there's a very interesting and simple relationship, which you wouldn't expect. And that's part of what the homework problem asks you to prove. Now, you can see that there are lots of possible applications of this. Any kind of priority queue in which when the server finishes its work, it does some other work and is unavailable at the main queue, well, that's a vacation model. And in fact, in the model I gave you, what I said here is the server doesn't go on vacation until the server's idle otherwise. But that doesn't have to be true either. You could have a system in which the server works for a while, then takes a vacation, then comes back and works for a while, then takes a vacation, and so on. So there are different ways to specify when the vacation is taken. There are different ways to specify how long the vacation lasts. And the objective is to be able to handle this all in one unifying framework. Now, one of the particular reasons for this, one of the real interesting applications, and the one that in fact motivated the vacation model, was what's called now a polling model. A polling model, you imagine there's a bunch of stations, and the customers arrive to the individual stations according to independent, different Poisson processes. So what you've got in effect is a bunch of queues. Each is an MG1 queue in isolation with its own service time distribution and its own arrival rate. But the queues interact because I don't switch from one queue to the next until this queue is empty, let's say. So in the polling model, I might serve all the messages that are waiting, and then when there's no more work to be done here, I switch to the next queue. And then I serve all the work that's waiting there, and then I switch to the next queue, and so on. So that from the viewpoint of an individual queue, the length of time I spend serving all the other queues can be viewed as a vacation. So I serve everybody here, then I take a vacation. The length of the vacation depends on how much time I spent here. There's an important dependency. Because if I spend a lot of time here, then during the time I'm serving, large queues are going to be developing here. The more queues that there are here, that is, the longer the queues are at these other stations, the more time it'll take for the server to cycle around, that is, the longer vacation it takes. The longer the vacation, the more customers will be waiting at the end of the vacation. The more customers that are waiting at the end of a vacation, the longer it takes to serve them, and then the more that are waiting here. So that the cycles are positively correlated, and you can't neglect the dependence between them. And the trick is to use the results of the vacation model to break up the analysis of a station into what happens when you're on vacation, that is, and what happens when you're not. One of the results that comes out of this vacation model is what's called decomposition. This is a key concept. And what the decomposition says, what we'll be able to prove, is that you can break, in a sense, you can break the analysis into two pieces, one of which has nothing to do with the vacation, and the other of which has to do only with the vacation and nothing to do with the queue. So you wouldn't think that you would be able to separate those things because they appear to be interleaved. But the mathematics shows they separate. And then the question is, OK, all you have to do then is figure out how the dependence among the queues affects the length of the vacation. So that's like the strategy, in a sense, for most of the rest of the course. We'll be putting together the pieces so we can get to do that. This is my particular research area now. So if people get interested in this, and you want to do a master's thesis or a PhD dissertation in this area, this is where the course is now going to stop from standard queuing theory and become an advanced course and be looking at research. OK, any questions? Or if not, we meet again on Monday, right? OK.